Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to apply the work energy theorem in cases where the gravitational field is not considered constant. So what we're going to do here is we're going to calculate what's called the escape speed for the planet Earth. So I've got a picture of the Earth here. The sphere is supposed to represent the Earth. I wrote some things down we're going to need. I know that the average radius of the Earth is around 6.4 times 10 to the 6 meters. The Earth has a mass around 6 times 10 to the 24th kilograms. So let me talk about what escape speed means. You've probably heard the old expression, what goes up must come down. That's not always true, right? When you throw, if you throw a surface from some sort of planetary body, if you throw some sort of object from the surface and you throw it faster, it's going to go higher. Throw it faster, it's going to go higher yet. Eventually, you can find a speed that you can throw an object at that it will break free of the gravitational influence of the planet and never come back, and that's called the escape speed. So that's what we're going to do here. In this example, we're going to imagine somebody throwing something from the surface of the Earth. I say throwing, but fired is definitely a better term there. We're going to ignore the effects of air drag, just because I want to demonstrate how the concepts fit together. Air drag is not important for that. I'll go ahead and comment at that at the end. And it's basically, we can treat this like a work energy problem, because it basically is, just like any other problem. Somebody throws a baseball or something up in the air, that typically can be analyzed with work energy. So whatever's being thrown, I'm going to imagine it being thrown from right here. I'm going to call that position 1. This is, in theory, just off the surface of the planet. It would have a velocity, which I would call v1. Right? Now, this object, imagine it thrown very, very, very fast. If I did kind of a motion diagram, it's covering lots of distance, going very fast. It'd be slowing down out here somewhere. I'm going to call this position 2 now. Here's our object at position 2. It's got a speed to the right now. I'm going to call that v2. Now, distances. Back to picture 1. From the center of the Earth to this object, there's a distance, and that's equal to the radius of the Earth. Right, then we've got the distance from the center of the Earth to position 2. I'm going to call that R2. And now I'm just going to go ahead and write out the work energy theorem. Right? PE1 plus KE1 plus work equals PE2 plus KE2. Now, I'm just going to go through term by term, just like we always would in any work energy problem. PE1. Now, gravitational potential energies, a lot of times, in most problems in physics, it's mgh. This is only true, however, if you're in a constant gravitational field. When you get to kind of a planetary type scale here, if we're getting far enough from the planet that gravity is not constant, this is not good enough. So we're going to use the more general form of potential energy, which is minus g, I'm going to put big M, little m over r. Now at position 1, the r, measured from the center of the Earth to this object, is equal to the radius of the Earth. All right, so this is basically, this goes in place of the mgh terms when gravity is not constant. Right? Position 1, we also have a kinetic energy, 1/2 mv1 squared. As usual, I'm going to hold off on the work term. For those of you who've seen lots of my videos, I like to talk about the work terms last. I'm just going to leave a space for it. All right, PE2. Again, big G, big M, little m over R2 with a minus sign in front of it. KE2, 1/2 mv2 squared. Right? Let's go back and talk about that work term. If we picture a free body of this object, just kind of generic, somewhere in the middle here, there's only one force, the gravitational force, right? The force of gravity. And it would be to the left in my picture. There's no other forces. Once this thing is, it's off the surface of the Earth, it's not in contact with anything, there's no other planets in theory in this example that are relevant. Now, this gravitational force is doing work, but that's what we're taking into account with the potential energy terms, right? That's what they do. The potential energy terms take into account the work done by the gravitational force. So there's only one force we've already taken into account, so we're going to put a 0 there. And here's our work energy theorem now written out for this problem. It's just like we always did. You know, if you've watched my previous videos about work energy examples, what did I do? I tried to do at least in every example. You draw a picture of the system at state 1. Draw a picture at state 2. Labeled it 1, 2. Draw velocity vectors, right? This has a velocity vector here at state 1. This has a velocity vector at state 2. Write out the work energy theorem. Evaluate it term by term. So really conceptually, this is no different than any other work energy problem we've ever done. The only difference comes into play here. Gravity is not constant, so we use Newton's theory of gravity to write the potential energy terms. Right? This is just the more general potential energy term under Newton's theory of gravity. Here and here. All right. So there's our equation here. Now I got to figure out what we're going to do with it here. Now, for starters, let's talk about these terms on the right. Escape velocity means it's never coming back, which means the radius is getting larger and larger and larger. In fact, how large? Well, we're going to imagine R2 going to infinity. If the radius becomes infinite, this term right here goes to 0. So this term will be gone. Now, the kinetic energy term won't. I mean, in theory, this is going to leave with some speed. But let's just kind of talk about how this guy, or this speed, is related to this one. Let's just say, for the sake of example here, that I put a number here like, I don't know, 10 to the 4th meter per second. I could backtrack that to this V1, and let's just say that I get something like, I don't know, 10 to the 6th meter per second. Right? If I come back here now and drop this, maybe 10 to the 3rd power, this is going to come out a little bit lower. Let's say it might be something like, I don't know, 10 to the 5th. And if I drop this one even lower, like 10 squared, this one might be 10 to the 4th or something. And then 10 to the 1st, and this might be, I don't know, 10 to the 3rd. All right. But eventually this is going to hit a 0, and I can't drop it any further. And this is going to be some number. It might be something like 1500 or something. This number would represent then the lowest possible speed and still have this thing break orbit and leave. And that's what the escape velocity is. So what we're going to do, because we're looking for the minimum possible speed to break orbit, we're going to set this to 0. So forcing this to 0 will make this the minimum possible speed. Oops. We'll make that a V-min. That'll get us the minimum possible speed to break orbit. So the new equation, we're going to have minus big G, big M, little m over radius of the Earth plus 1/2 m V1 squared equals 0 on the right-hand side. So now it's just a matter of solving this for V1. I notice that the mass is the same. This little m is the same, so that cancels. We can solve this for V1, or I like to write V1 squared. That's going to equal 2 big G, big M over R, radius of the Earth. And now it's just a matter of putting in the numbers here. So this is going to be 2. This is going to be 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. There's your G. Mass of the Earth, 6 times 10 to the 24th kilograms. And then over, that's all over the radius of the Earth, 6.4 times 10 to the 6 meters. So if we work this out and you solve for V1, and don't forget to square root it, you're going to get about 1.1 times 10 to the 4th meters is what should come out of that, I believe. I think I've done that calculation lots of times. And I like to write this as 1.1 is about, well, how do I like to write this? It's about 11 times 10 to the 3rd meter per second, not meters, meter per second. Or in other words, about 11 kilometers per second. I think it comes out to be like 11.1 or something. I'm not concerned about the 0.1. So the V1 here is around 11 kilometers per second, give or take. Now it's pretty fast. 30-06 fires a bullet at a little less than 1,000 meters per second, or about 1 kilometer per second. So that's about 11 times the speed of a 30-06 round. Now, let me go back to our assumption here. This was launched from the surface of the Earth. If you launched a particle with this type of speed in air, it would vaporize. I mean, that's what, when you watch shooting stars come in at night, that's kind of what's happening. Rocks are coming in, hitting the atmosphere at speeds measured in kilometer per second, and they basically vaporize. So our no air drag assumption here, or little air drag, is not a valid assumption for this. I mean, air drag is a huge, very significant force when you're talking about 11 kilometer per second. But I still like the example. It still works out. It still very nicely shows how you apply work energy in Newton's theory of gravity here, when gravity is not constant. So anyway, if the Earth had no air around it and you launched a particle at 11 or so kilometer per second or faster, it could leave the gravitational influence of the planet. Anyway, hope this example helps. Have a great day.